Right. Hi, everyone. Good morning. Welcome to the Cryosphere Pavilion on the last day of COP29, and thanks for being here. Today, we'll have a few sessions from some of our early career scientists with the pavilion. And we'll start off with Emma Robertson, who's a PhD candidate at the Alfred Wegener Institute in Germany. And she will be talking about freshwater fluxes in the Southern Ocean. And I'll let Emma take it further.
Okay, thank you, Shiva, for the introduction. So yeah, I'm a PhD candidate at the Alfred Wegener Institute, and I'm also at the Ludwig Maximilian University of Munich, and I study physical oceanography, particularly in the Weddell Sea. So I want to start off a little bit talking about the role of the Southern Ocean in terms of global ocean circulation. And this figure here that I show, we've centered by Michael Meredith. It shows Antarctica and the Southern Ocean at the center of the world in terms of global ocean circulation to illustrate the importance of overturning waters in the Southern Ocean and Antarctica as far as global circulation is concerned. This is important not only for the transport of nutrients, but also for the storage of heat and carbon in the ocean. And so the reprocessing of water masses around Antarctica removes heat and carbon from the atmosphere, storing it in the deep ocean for up to centuries. Went a little bit too fast. Okay, we're back. So talking a little about the role of salinity in terms of global ocean circulation, salinity is a fundamental parameter in terms of vertical mixing throughout the ocean. And salinity variations in the Southern Ocean are what drive this exchange of heat and carbon. The salinity variability of water masses in the Southern Ocean is primarily driven by sea ice formation, sea ice melting, as well as glacial melting, as well as other atmospheric and glacial interactions with the ocean. So here, what you see on this map is temperature-dominated regions in terms of vertical mixing. And at the poles, both in the north and the south, you see where we have salinity-dominated regions in terms of vertical mixing. This is important, particularly for looking at circulation and salinity changes in the Southern Ocean. When we look at water masses such as Arctic bottom water here that you have in this reddish orange square, which are really important in terms of global circulation. So you might be asking, why do we need to understand Antarctic bottom water freshwater fluxes and their changes? One thing is that Antarctic bottom water is a major component of global ocean circulation. And also to monitor the Antarctic contribution to sea level rise and ocean circulation. When I talk about the importance of sea ice processes, glacial melt processes, in terms of influencing the salinity of the Southern Ocean, this is particularly important when we think about rapid declines in sea ice over the years, particularly with this sea ice minimum that we experienced in 2023, which still hasn't recovered. Before we wanted to move on, I wanted to do a quick quiz for some folks in the audience about what type of sea ice this is in the picture behind you. So we have 4 options, A, B, C, and D. Can anyone put their hands up for A? For B, C, and D. All right, so if you picked B, pancake ice, you were correct. Okay, moving on, talking a little bit more about the project that I'm working on, which is SOS iClimate, where we study Southern Ocean salinity and it's using isotopic fingerprints and its impacts on global climate. In order to study the Southern Ocean, we need observations. So one of the biggest parts of this project is collecting novel data and building a comprehensive database of these seawater isotopes. What you see here in this magnifying glass are these seawater isotopes that we use in order to study salinity changes, notably oxygen-16 and oxygen-18. And these allow us to sort of fingerprint and identify the different sources of fresh water in Antarctic bottom water and other water masses. So whether the fresh water is coming from glacial meltwater, coming from sea ice melt or formation, or coming from atmospheric processes such as precipitation and evaporation. So part of building this database, I guess going back a little bit, is that these observations of seawater and Antarctic bottom water are really important. But part of the problem that we have with working in the Southern Ocean, with it being so remote and also particularly hostile environment, is that we typically only get observations every 5 to 10 years. We're working on that as far as collecting and creating a database of all available observations from labs around the world, so including labs in UK, Germany, China, France, and Japan. In this upcoming winter or austral summer, we'll be participating in an expedition. We'll be doing some seawater isotope intercomparison, collecting water isotopes for different labs in order for those samples to be sent out and observed in labs around the world. So moving on to what we do with these observations, I mostly work on the second part of the project where we use these observations to identify fingerprints of changing ice in a freshening ocean. There's a couple different regions around the Antarctic continent where Antarctic bottom water is formed. I'll be primarily talking about the Weddell Sea. I'll be talking about the Weddell Sea. The Weddell Sea is responsible for nearly half of all Antarctic bottom water export and formation. But at the same time, Weddell Sea bottom water has been experiencing a sharp decline in its volume. And we think this is likely driven by changes in sea ice regimes. So talking a little bit about how Antarctic bottom water is formed, you see in red this circumpolar deep water moving towards the ice sheet. And as this circumpolar deep water moves towards the ice sheet and interacts with these open areas of ocean free of sea ice called coastal polynyas, it exchanges heat with the atmosphere, causing freezing of sea ice. And when sea ice freezes, you get what's called brine. You get what's called brine expulsion, where when the sea ice freezes, you get a release of that salt from the sea ice, causing dense salty water to sink below the ice shelf and eventually flow off the continental shelf and circulate throughout the global ocean. But over this period of time, over the past couple of decades, we've seen sea ice export decrease, partly because of a decrease in these katabatic winds that you see up top in this blue arrow right here, that would typically push sea ice out, from coastal polynyas and out into the open ocean. But with a decrease in these winds, less sea ice is being pushed out, which leaves less area of open ocean for sea ice to be formed. As a result of that, one of the questions that we're asking is whether we can quantify freshwater signals in Antarctic bottom water from these sea ice-driven processes. So, looking at observations of Antarctic bottom water, I've broken them down into different regions, which are colored by different clusters on the map on the left, and which in the time series on the right, showing the sea ice fraction of the sea ice melt fraction that contributed to the Antarctic bottom water. And so what you see here is over this period of the past couple of decades where we saw sea ice export decreasing, we also saw an increase in the sea ice melt fraction that was present in Antarctic bottom water. And over this same period of time, looking at the water isotopes, we also saw enrichment of these water isotopes, which is indicative that sea ice is driving these processes rather than glacial melt driving these processes. if we had expected that glacial melt was driving these processes, we would actually expect the arrow to be pointing downward and that you would see a decrease in this delta 18 in the seawater isotope signal. Looking also at the salinity, in most regions, we also see salinity in most clusters. In most regions of the Weddell Sea, we also see salinity decrease over this period of sea ice export decrease. So a quick little summary of what we think is happening as far as it's agreeing with literature and the work that we've done. We know that sea ice export has decreased, which we think has led to a decrease in salt input into Antarctic bottom water. And the resulting observations in Antarctic bottom water are both enriched in delta 18, so these seawater isotopes, and also have lower salinity throughout the years. So some of our conclusions are that these changes in salinity appear to be driven by sea ice freshwater fluxes. And the implications of this are that declines in sea ice are likely to have strong effects on Antarctic bottom water formation and volume. I just wanted to end again by showing this figure where we see progressively throughout the years declines in Antarctic sea ice maximum. And if this trend continues, what we can expect is also potentially decreasing export of Antarctic bottom water and potentially pretty dangerous effects and how this affects global ocean circulation. So yeah, I finished there and I'm happy to take questions. I've also put my email up there if you would like to stay in touch, and thank you all for listening. We do have some observations from East Antarctica from a cruise that my supervisor participated in, where they actually did a whole Antarctic circumpolar expedition. Part of the reason I'm focusing on the Weddell Sea is because I have the densest observations there in terms of both time and space. In Eastern Antarctica, I have observations, at different points, maybe kind of once. And so it's a little bit difficult to compare what's happening in time there. So it would be nice to have some observations in Eastern Antarctica in order to look at how potentially Antarctic bottom water transport or volume or formation is being affected there by changes. But yeah. Yes. I suppose what I'm expecting when we're finally able to analyze the samples is that we'd see probably a decreasing, potentially a continued decrease in that salinity and perhaps more evidence of the sea ice melt fraction within Antarctic bottom water. What would be interesting though is that there's one region that we found that was less vulnerable to those salinity decreases. And so it would be interesting, as we're going to be making repeat observations there, whether or not that's something that has continued, whether that area has continued to see an increase in salinity where other regions haven't, or whether this area is now experiencing the same sort of decreases in salinity.
I have a little question. You showed the isotope plot where there was an enrichment in the surface water isotopic molecules. Could that be just an evaporation signal?
Pardon?
Could that just be an evaporation signal, that is ocean evaporation? Because evaporation causes enrichment in isotope.
That could potentially be it as well. Part of, at least right now, my hypothesis, where I've also looked at the glacial melt fraction, or the meteoric fraction of that, of those Antarctic bottom observations, is that where I see the increase in the sea ice melt fraction, I also see a decrease in the meteoric fraction. So that includes any glacial meltwater, but also atmospheric processes as well. But it would be interesting definitely to look into. I think that could potentially explain things
because
as well.
the enrichment is not 2 joules, right? It's just 0.1 per mil, right? So it's not big.
Yeah. Okay, then. All right. Thank you all for your questions. Yeah. Okay.